Alright, so we'll just answer this interesting question. Um, on atomic structure, if you have one more of hydrogen atoms with their electrons in n is equal to 1 energy level, what is the minimum number of photons? So that's the first question. You would need to interact with these atoms in order to have all of their electrons to be promoted to n is equal to 3. What wavelength of light would you need to perform this experiment? So answering three questions. The first question is, what is the minimum number of photons that are required to lead to a transition from the first to the third for one more of hydrogen atoms? Okay, so Avogadro's constant would tell us to say 6.022 by 10 to the power 23. So in this case, we're dealing with one to know how many hydrogen atoms we would have in a mole. So it will just be atoms per mole. So a mole of hydrogen would actually give us that number of atoms. Okay. So if we are to look for the number of photons, we understand that in each transition, this one from n is equal to 1 to n is equal to 3, we would need one photon minimum. Okay. So one photon is required for a transition to occur from n is equal to 1 to n is equal to 3 per atom. So the minimum number of photons would need for each atom would therefore be equivalent to the same Avogadro's constant. So that would be 10 to the power 23 photons. Okay. So I've explained that for every transition, a minimum of a photon is required. Okay. And since we've got 6.02 times 10 to the power 23 atoms in a mole of hydrogen atoms, so it's actually going to be the same value for the number of photons required. Okay. And then the second question says, actually, how many questions are we answering? What is the minimum number of photons you need to interact with? Okay, so the second is, what wavelength of light would you need to perform this experiment? Okay, so we use like Rydberg's equation. The energy that would be required, of course, would be 2.178 times 10 to the power negative 18. This is in terms of joules. So that would be 1 over the 1 squared minus 1 over 3 squared. So where the 1 is actually representing the initial, then the 3 is representing the final. Okay, so that's a formula that I'm actually using. Of course, this formula comes from the combination of this formula and also the Liebig equation that includes the wavelength, and that's Liebig's constant, 1 over the initial minus 1 over the final squared. Okay, so that's the equation we're working with right now. And so if you try to make energy subject, you end up with this formula in terms of joules. Okay, so in the brackets we're going to have, so that would be 1 minus 1 over 9, that would give us 8 over 9, and then you can multiply that with what we have. So 2.178 times 10 to the power negative 18 multiplied by 8 over 9, I'm getting 1.936 times 10 to the power negative 18 joules. Okay, so we determine the amount of energy that is actually required to transition an electron from the first energy level to the third energy level. This is the amount of energy associated. Now we're interested in the wavelength. Okay, so now if we go back to our formula, I don't even know why I've wasted much time, because Liebig equation itself would have answered this question directly. But anyway, we've already done it. So energy is equal to hc over the wavelength, and then if you make the wavelength the subject, you're going to have hc over the energy. So what are we trying to say here? What we're trying to say is the wavelength is going to be Planck's constant, which is 6.626 times 10 to the power negative 84, multiplied by the speed of light, which is 3 times 10 to the power 8, divided by the energy 1.936 times 10 to the power negative 8. And so perform the calculations there. The wavelength that I'm getting is what are you getting? I'm getting in fact, to make the value is somewhat small, 0.00 something. Now to make things easier for ourselves, we can convert to nanometers, so that we just multiply by 10 to the power 9, and after multiplying by that I'm getting 102.676. okay, so you can just end up with just 3 significant figures. So 103 nanometers, that's the wavelength associated with the light that would give a photon for each transition. Okay, so that's it for this question.